Can everyone see my slides okay? Okay, lovely. Okay, so today I have a story for you with the title Spectral Non-Backtracking Spectral Clustering of Non-Uniform Hypergraphs. And this is a story about a lot of things. Actually, it's a story about some linear algebra. It's a story about community detection in hypergraphs. It's a story about an algorithm, and it's a story about some conjectures that we hope are going to attract some attention and work from smart people in the future so that those conjectures can become knowledge. So there's a lot of things in this story. I really enjoy this work. It's some of the work that I've done that I'm most proud of. And I hope that you'll enjoy this story too. And maybe if you feel moved, you'll work on some of these conjectures and you can be the one to prove them. So here we go. This story revolves around what I'm going to call the hypergraph clustering problem, but you might also think of it as the hypergraph community detection problem or really anything else. So the hypergraph clustering problem begins with some hypergraph data like I have on the top right here. And the problem says, hey, given some hypergraph data like this, I'd like to assign each node to a cluster of related nodes, where we often cash out the term related in terms of densely interconnected. So when we do community detection, that's often our idea of being related. There's a lot of ways to do this problem, all of which, or most of which, start with something like on the top right and end with something like on the bottom right, where we have the same data, but to each node, we've assigned a label here represented by a color. And in this particular case, this is a pretty small hypergraph. It has only 2 and 3 edges, only 8 nodes. We can kind of eyeball it and find a reasonable partition of the nodes in a way that looks like, well, each node in each of these clusters is more densely connected to other nodes in that cluster than it is to nodes in the opposite cluster. So this one we can kind of eyeball. Of course, in actual applied science, we can't eyeball it. We have larger data. We have more complicated data. The situation is not as clear. We need some algorithms. So the emphasis for today is on spectral algorithms, but also what those spectral algorithms can tell us about the theoretical limits of our ability to actually do this task. And if you're interested in some honestly pretty gory details about the story I'm going to tell, then you can find an archived preprint by the same title, Non-Backtracking Spectral Clustering of Non-Uniform Hypergraphs. Okay, so before we jump really deeply into the hypergraph problem, I wanted to remind you of some things that we know about the graph problem. So in the graph problem, we actually have this really nice body of theory around when it's even possible to solve this problem, when it's even possible to do clustering or community detection. So the place in which this is usually formulated is in a stochastic block model with 2 groups, the kind of thing that we visualize on the top right there. So here we have a red group and a blue group. And in these groups, nodes in each group have, in expectation, A edges connecting them to other nodes within that group. So every red node has, in expectation, A edges connecting it to other red nodes. But then nodes also have, in expectation, B edges connecting them to nodes in the opposite group. And so usually we imagine B being much smaller than A, here showing sparse connections between groups. And our aim, algorithmically, is to either recover these groups exactly, that's the ideal case, but often we actually settle for a weaker task, which is simply finding a clustering that is correlated with the actual groups. So we imagine erasing these labels and we design an algorithm to find new labels, and we'll actually settle in what we call the detection problem for just finding a clustering that's correlated with the ground truth. It doesn't have to be right, it just has to be reliably better than random chance. And it turns out, from a pretty nice set of conjectures from a paper from about 10 years ago, only pretty recently proven, actually, it turns out that this problem has an interesting detectability threshold, which is that you can only find clusters correlated with the ground truth. That's possible if and only if, as the number of nodes grows large, the parameters A and B satisfy this relationship, which we can actually interpret as a signal-to-noise relationship. The signal-to-noise ratio needs to be large enough. So on the bottom left here, that relationship says something interesting because notice that intuitively, if A and B are different but relatively close to each other, you can have this ratio be smaller than 1. And that implies that even when there's a systematic difference between the communities, they are indeed more densely connected with each other than within each other than they are between each other. Even when there is a systematic difference, if that systematic difference isn't large enough, this problem is information theoretically impossible. Can't do it with any algorithm. So for an example of what this looks like, if you actually sort of plot the performance of an algorithm as a function of these parameters A and B, you see something like I have on the bottom right here. This is a figure from Anadakadi and Newman in a paper from 2012. What your algorithm is going to do is it's going to do no better than random chance for certain parameter regimes, and then you're going to see this nice phase transition where suddenly your algorithm begins to recover clustering that is correlated with ground truth, not perfect, although it might become asymptotically perfect, but it'll be at least correlated. So one of the sort of starting insights from this work that inspired the story I'm going to tell you today is that in this work, it's not just that sort of we have this abstract possibility of finding these clusters when this ratio is large. It's actually that this ratio was initially conjectured, and since there have been proofs around this, kind of the way we figured out this story was through the lens of matrix methods. So folks looked at eigenvector methods for studying this clustering problem, and it was proven that these matrix methods are actually asymptotically optimal in the sense that as n grows large, they can find clusters correlated with ground truth whenever that task is possible at all. So they're asymptotically optimal. They're not necessarily optimal for any specific data analysis task, but from a theoretical perspective, if this problem is possible at all, there are certain matrix methods that can do it. You calculate the right matrix, you calculate the right eigenvectors, the details depend on exactly which matrix you choose, and then those eigenvectors will tell you information about the clusters, and that's always gonna work in the sense of getting you something correlated with ground truth. So this is what we know about graphs. There's a detectability threshold, and matrix methods are asymptotically optimal for reaching that detectability threshold. So what about hypergraphs? How do we actually find the limits of this problem in the hypergraph setting? That's going to be the main inspiration today. And because we know that matrix methods are asymptotically optimal in the case of graphs, the approach that I'm going to tell you about is an approach that goes through matrix methods. And so that's why the title of this talk is Non-Backtracking Spectral Clustering for Non-Uniform Hypergraphs. To kick us off, I want to compare against another hypergraph clustering algorithm, and we're going to do it in a kind of theoretical synthetic test bed. So here's a synthetic test bed for hypergraph clustering. This is a parameterized model in which we have two parameters, P2 and P3. P2 is the fraction of two edges that are going to join nodes in the same cluster to each other. P3 is the fraction of three edges that are going to join nodes in the same cluster to each other. For example, when P2 and P3 are both large, we have this kind of classically clustered situation up here. This is the kind we can eyeball easily and it's all good. On the other hand, if, for example, P3 is large, but P2 is small, that means we expect three edges to stay within their clusters. On the other hand, two edges are going to more frequently move between clusters. And so that's what happens when P2 is small. And then we can vary our parameters in other ways. So down here, for example, both P2 and P3 are small. And so all edges tend to run between clusters. So this is a little parameterized test bed in which we can try different kinds of clustering algorithms to see how they do. So we introduced this test bed in a paper with Nate Veld and Austin Benson. And in this paper, we derived a modularity optimization method for clustering hypergraphs. And this method, kind of the best thing about it is that it's fast and it works on pretty large data sets. But one of the things that we kind of learned interestingly about this method is that in this test bed, it gives results that I think are frankly kind of bizarre. So I'm showing you now what I think is the weirdest plot that I've ever put in publication. I see a hand there. Yeah, Tim.
Yeah, Phil, is it okay if someone asks a question?
Oh yeah, go for it. Yeah.
If you can speak loud and we
Can you hear? Can you hear?
Barely.
Okay. I was just gonna ask, you say that in the lower left with Chodrow, you expect most edges to run between clusters? When you have low P2 and low P3, I would still expect most edges to be within or percentage to edges as compared to between. The percent is as compared to between clusters.
Yeah. So here we're going to have a fixed number of edges or a fixed number of edges in expectation. So we're going to have the same number of edges overall, and P2 and P3 are just going to control whether those edges tend to be more often between or within clusters.
Okay.
Yeah, thanks for the clarification. That's helpful. So when we turn this modularity algorithm, whose details I'm not showing you because it's not the point for today, when we turn this modularity algorithm on this test bed, we get this kind of bizarre looking plot over here, where what we do is for each of these parameter settings, we did 100 pixels by 100 pixels here, so the 100 different values of P2 and P3. For each of those pixel settings, we did 10 runs, so we generated 10 hypergraphs with those parameters, and then we used modularity maximization to try to recover our clustering. And what we found is that our algorithm performs pretty well in some settings. So for example, you can see on the far right, when P2 is very large, we seem to do okay. When P3 is very large, we seem to sometimes do okay, but not if P2 is between the values of 0.5 and roughly 0.7 or so. There's something funny going on in the bottom left here. So overall, I think this is a very strange set of results, actually. There's all these gaps in the ability of this algorithm to detect clusters where really there kind of shouldn't be from a mathematical perspective. So for example, if you look at the bottom left, you can see that this algorithm actually made some attempts to detect clusters when P2 and P3 are both very small. This attempt has not succeeded systematically, but in some sense, if you know that all the edges are running between clusters, that's a very strong signal that you can use to fully identify the clusters, and so you should be able to do better than this. So overall, this was something we learned from, but in looking at this plot, I kind of said, okay, well, this is kind of interesting, but surely we can do better on this synthetic test bed. And so I want to emphasize that by better in a lot of this talk, I'm going to mean, can we do better in sort of the sparse synthetic hypergraph setting? I'm mostly not talking about data analysis, although I'll show a data analysis example toward the end. So how are we going to do better? Well, that's the story that
We had one more question, if that's okay.
Oh, yeah, go for it. Yeah.
Sorry, it's hard to see.
Sorry, so just a question. So am I right to understand that so you created the hypergraph, right? And then you form them into graphs, and then you ran the community detection on the graph that is basically obtained from the hypergraphs. Is it the way that you've been using the Louvain type algorithm on your data?
So right now what we did is we have a Louvain type algorithm that just works directly on the hypergraph data. And so we were running it directly there without doing anything converting to a graph. Is that
okay?
Is that your question?
You mean that you have a modularity that was defined for the hypergraph directly?
Yeah, it's explicitly a hypergraph modularity.
Okay.
Yeah. So we wanted to do better than this, and so in order to do better than this, I assembled honestly an awesome team. Really, y'all, especially if you're early career people, my advice is to find yourself collaborators who are amazing, like these collaborators are. So the team for this paper is really two of my favorite people to work with in the world. That's Dr. Nicole Eichmeyer in the Department of Computer Science at Grinnell College, and Dr. Jamie Haddock in the Department of Mathematics at Harvey Mudd College. So together, we've written this by now quite gnarly manuscript that you can find on arXiv, Non-Backtracking Spectral Clustering of Non-Uniform Hypergraphs. And so this is now the beginning of the story after the prologue. So the prologue is we have this very bizarre result using a modularity method. Can we do better using a different kind of algorithm? So we're going to try to do spectral algorithms, and because we know that matrix methods can be optimal in the graph case, our hope is that we'll learn something about the fundamental limits of this task using these spectral methods. But there's already kind of a difficult set of questions to address. Namely, how do you even put together matrices for hypergraphs? It's actually kind of non-obvious. So there's a few candidates. We can transform the hypergraph into a graph. There's lots of ways to do that. So we can do clique projections, we can do star expansions, we can do bipartite representations. For all of these except bipartite representations, you usually lose multi-way information, and so we can kind of expect that anything that loses information is probably not going to be optimal. On the other hand, if we want to do kind of spectral stuff, eigenvector things, we can also construct tensors. So if I have 3 edges, I can store all those 3 edges in an adjacency tensor of order 3. I can store the 4 edges in an adjacency tensor of order 4, and so on. This is a pretty reasonable thing to do, but there's an issue there as well if we want to do spectral things, which is that there's now a reasonably well-developed theory for eigenvectors of tensors, but not for eigenvectors of sets of tensors, which is what we have here. So if we want to actually represent the higher order structure in this hypergraph as a matrix, we have some work to do. The way that we're going to do it here is we are going to consider the non-backtracking operator. So whereas something like an adjacency matrix operates on pairs of nodes, it tells you whether or not there's an edge between 2 nodes. The non-backtracking operator operates on edge node pairs. So I take 1 edge and 1 node and a second edge and a second node. And my non-backtracking operator tells me about the relationship between 1 edge node pair and another edge node pair. The symbols here defining this operator are, in my opinion, pretty unenlightening. The idea is simply that I can hop from a node to node in a hypergraph, and I can do those hops in such a way that I never hop to 1 node and then back to that same node, and I never hop twice within the same edge in a row. So I can walk in my hypergraph without backtracking, is the intuition here. I can do walks in my hypergraph without backtracking. I can do it without visiting the same edge consecutively or without visiting the same node consecutively. So the hypergraph non-backtracking operator is an operator that encodes these kinds of structured, well-behaved walks. This operator was proposed for hypergraphs by Christopher Storm in 2006, and subsequently, I'm going to say, rediscovered without citation by a group in 2015. So we're not introducing this operator, but we are trying to go a little deeper into the kinds of things we can use it for. So why is this a good operator to consider in the context of community detection? Well, one thing is a theorem. If you consider a stochastic block model with 2 equal-sized clusters and you control the k degrees of the nodes, so we say that in this stochastic block model, every node is going to have in expectation a sub k in, no ins and outs, just a sub k and b sub k for notation. Every node is going to have a sub k, edges of size k within cluster, and b sub k, edges of size k between clusters. If we control these parameters, then there's an in expectation eigenrelation that we can derive, where we actually know the expected value of the eigenvalue. I've called it beta here. It's 1/2 times the sum of the differences between the within cluster degrees and the between cluster degrees. And we know that the associated eigenvector is correlated with clusters. So on the right, I've shown you kind of the schematic picture of this. So in the top, I'm pointing you to beta. Beta is the community correlated eigenvalue here. This is a plot of just all the eigenvalues of a relatively small matrix. You can see that most of them are concentrated in this nice disk. There's one on the far right, that's the largest real eigenvalue that is correlated with degree information but doesn't really tell you anything about the clusters. Then in the good case, and I'll say more about what I mean by good case later, in the good case, there's going to be another real eigenvalue that's going to be separated from this disk, where if you take that eigenvalue and look at its associated eigenvector, you have to do a little bit of summing up in order to get things on the node level. But you do the summing up and you see a picture like on the bottom right here, where in this hypergraph with 100 nodes, if I look at the signs of this aggregated eigenvector, I can see that the signs correlate to the partition that I planted. This partition in this case is represented by that dashed line, first 50 nodes in one cluster, last 50 nodes in the other cluster. So if I clustered based on this eigenvector, I would be able to learn something about the clusters, and I would be able to get a result that is correlated with ground truth. So this operator is already something that we know is going to be helpful for us. We know that this non-backtracking operator is going to tell us something about the clusters if the clusters are detectable, if we're able to find this nice eigenvalue and get something out of it. Now, a bit of an issue here already is that this operator, I sort of glossed over this when introducing it, but this operator can be quite large. So B is this matrix. It's indexed by edge node pairs, which means that it's of size m times the expected value of k, where m is the number of edges and k is the average edge size. So for example, a small data set, something like the contact high school data set, which is something we often use in hypergraph experiments. This kind of data set, it has about 300 nodes, about 8,000 edges, and an average edge size about 2.5, which means that the non-backtracking operator for this matrix is already of size about 20,000 by 20,000, which is a pretty chunky matrix and poses some challenges for computation of eigenvectors just already. We can do it, but it's not fast like you would want something to be on a 300 node data set. So these eigenpair computations are going to get expensive fast. So from a computational perspective, fortunately, there is stuff that we can do. So there's this nice class of theorems called Ihara-Bass theorems, and there's an Ihara-Bass theorem for this operator as well. And what this Ihara-Bass theorem says is that, hey, if you have an eigenvalue of this non-backtracking operator B, then you can put it into one of two cases. So in the first case, that eigenvalue has one of a few specific values, 1 minus 1 minus 2, all the way up through 1 minus the largest edge size. And in this case, the corresponding eigenvector carries no structural information about the hypergraph, useless for community detection. That's one case. Or second case, you can actually compute that eigenvalue from a more complicated looking but smaller matrix. Excuse me, so here B prime is this more complicated looking but smaller matrix that has the same interesting eigenvalues and related interesting eigenvectors to our original matrix. And so here, just to unpack some of the notation, K bar is the number of distinct edge sizes and N is the number of nodes. A and D are block adjacency and degree operators. K is a little diagonal matrix that lists the possible edge sizes. We have identity matrices and this circular times. That's the Kronecker product, the tensor product for matrices. So we can actually shrink our matrices down in order to make our computation a little faster. We can still get the same eigenvalues and we can get the same eigenvectors up to some simple transformations. The nice thing about this proof is that it's actually pretty elementary. So what you do is you write the non-backtracking operator B in terms of several operators that we called ST and R here. And these operators, they have this relationship to B, B equals ST minus R, but they also have other useful relations. If, for example, if you multiply T and S in the opposite order, you get this block adjacency operator. So you sort of play shenanigans like this to use your matrix identities. And then you just use a simple determinant identity. This is called the push-through identity, where we actually take B on one side and we can express B in terms of a product of two determinants there. What happens when we actually do this is that we find ourselves with the characteristic polynomial of B prime as one factor and an uninformative polynomial as the second factor, which means that we can nicely factor the characteristic polynomial of B and learn things about a spectrum. So nice little consequence here is for computation, which is that on that same data set where the overall non-backtracking operator B would have about 20,000 by 20,000 dimensions, in this case, this Ihara-Bass theorem allows us to instead compute on a much smaller matrix with less than 2,000 by 2,000 rows and columns, which for many eigensolvers is going to be 100 to 1,000 times faster. So this is a nice instance of sort of fun theoretical math, fun linear algebra in the service of computation that we can play with. So this kind of suggests a first algorithm for the clustering problem. So I've kind of been hinting it, and now I'll just sort of state it formally. So the first algorithm, we can compute the second eigenpair of either the original operator B or the smaller operator B prime. If the corresponding eigenvalue is real, we will take the corresponding eigenvector. We need to separate it into two parts, alpha and beta, and then we're going to take alpha and we're just going to sum it over edge sizes. What that means is the result is going to be at the level of nodes. So we're going to get all these numbers, one for each node. And then by inspecting the sign of those numbers, we'll be able to make a decision about which cluster to assign it. So first algorithm, spectral algorithm based on the hypergraph non-backtracking operator. Let's try it. So we've been playing with this test bed, and as you remember, kind of our motivation was to do better than this very bizarre modularity maximization plot. And so when we try the algorithm that I just described for you in this same synthetic test bed, we get a very different looking result. So here it is. So there's kind of some interesting things to unpack here. So on the one hand, we observe this is a much more reasonable looking plot in some sense. It doesn't look like something that just would have flagrant errors in it, even though I promise we check the modularity one a lot. This one sort of looks reasonable. It doesn't look like there's any like very obvious weird gaps where the algorithm clearly should be succeeding. We see these nice smooth boundaries between success and failure. It looks like they might be lines. We'll come back to that. Small problem, though, is that if you remember the modularity plot, there are places where that Louvain algorithm was actually succeeding, but this algorithm is failing. So these white question marks indicate two of the places where we know it's possible to do better on this problem because the modularity algorithm does it, but this spectral algorithm is not doing it. So we know now there's a gap between what we aspired to and what we've achieved, because we know that matrix methods should in some sense be asymptotically optimal. This matrix method is clearly not asymptotically optimal because it's just flagrantly failing in places where we know it's possible to succeed using other algorithms. So we have made progress, we've learned some interesting things, but there is a lot more that we need to do. So kind of following the historical development of how we learned about detectability thresholds for graphs, we are going to take a detour into belief propagation. So belief propagation is a lot of things. It's this kind of really interesting and rich subject. So belief propagation, kind of originally, it's the cavity method of statistical physics. Belief propagation is an approximate method for what I used to call statistical inference, but now I'm a computer scientist, and so I say machine learning instead for branding reasons. And it's a discrete time dynamical system. So it has all these facets. It's a statistical physics calculation method. It's a statistical inference or machine learning method. And it's a discrete time dynamical system. All of these things are true about it. And so in some sense, we can kind of use these different perspectives in an effective way. So formally, for belief propagation for the clustering problem from a stochastic block model in hypergraphs, what we do is we iterate these two horrible updates to convergence. So we update mu, all these variables mu in terms of all these variables nu, and then we update all these variables nu in terms of the updated mu's, and we just do this over and over and over again. And here, there's one variable mu and one variable nu for each node, edge containing that node, and cluster. So there's a lot of these variables to update. The math looks horrible. It is horrible. And this actually reflects the fact that it's very expensive to do this computation on hypergraphs. So the math looks horrible for hypergraphs because it is horrible, and including computationally for hypergraphs. In terms of what we would get out of this if we were able to do it, what you would pay attention to is the mu's. So mu IRS is node I's confidence that it belongs to community S based on the other nodes in the tuple of nodes R. what we would do is iterate to convergence and sum all the mu's across tuples R, obtaining node I's confidence that belongs to community S, and that would be our final answer from belief propagation. But there's a lot of junk in the way, and it's just really hard to actually do this computation for large hypergraphs. So fortunately, this is where we emphasize the discrete time dynamical system perspective. We can actually learn something about the behavior of belief propagation by doing discrete time dynamical system techniques. And so what we're going to do is we are going to linearize around a fixed point using sort of really nice standard techniques. So theorem, if we consider a stochastic block model in which every node has the same expected number of attached edges, and the expected degree does not depend on the number of nodes n, then and this is all approximate and with high probabilities n grows large. With high probabilities n grows large, there's an approximate fixed point that I'll call x bar. And this x bar is uninformative. It's neutral between the clusters. It contains no cluster information for any of the nodes. And furthermore, when we consider the Jacobian matrix, the derivative around this uninformative fixed point, there are actually entries that are vanishingly small, except for a specific block that has the form at the bottom here. So this is J, which is the block of the matrix that I'll care about. J is the sum over edge sizes of a Kronecker product between a matrix that I'm calling CK, that I'll show you in a moment, and the matrix BK. And BK here is the Hashimoto operator, or non-backtracking operator, restricted to edges of size k. So previously I've been considering one big operator for every edge. Here I'm considering lots of little operators for each different edge size. And what I'm doing is I'm combining it using the Kronecker product with CK. CK is a matrix of parameters that depends on the stochastic block model P. You can think of it as depending on the P2 and P3, those kinds of parameters that control the expected number of within and between cluster edges for each size k. And then finally, again, the circular times is the Kronecker product. So what happens here is that when I linearize my dynamics around this uninformative fixed point, I obtain this matrix that has a structure that I can separate into contributions from statistical parameters and contributions from the core hypergraph structure represented by the non-backtracking matrix. So what I'd like to do using discrete time dynamical system stuff is I'm going to look for the eigenvectors of this matrix corresponding to unstable perturbations in the dynamics as represented by eigenvectors with eigenvalues that are large in magnitude of this matrix. Now, pause for an issue, which is that last time the matrix B was kind of inconveniently large, and the matrix J has only gotten larger. So we actually have the same computation problem as before. Fortunately, we have a similar solution as well. We can actually cheat by computing with, again, a much more complicated looking, but actually smaller matrix. This proof is honestly a little bit of a nightmare, so I'm not even going to tell you very much about it. But it uses a lot of the same tools from the similar proof from last time. So this is something like an Ihara-Bass theorem for this linearized belief propagation Jacobian. So we can compute either on the Jacobian itself J or on this smaller, denser matrix J prime in order to obtain the eigenpairs that we want to. With this tool, we are able to construct a new algorithm. So this is an alternating algorithm for belief propagation hypergraph spectral clustering. So here's the jam. What we do is we are going to use the spectrum of this matrix, J, or its smaller relative J prime, as follows. We're going to start with an initial guess for the parameter matrices CK. These are the statistical parameters. We can just sort of guess at random, or if we have some kind of reasonable hypothesis, we can start there. Then we form this matrix, either the full matrix J or the smaller matrix J prime. We look for all the real eigenpairs, lambda V, where lambda is larger than 1 in magnitude and real. And the reason that you need it to be real is related to the statistical properties of belief propagation, because you can't have complex probabilities. So we look for the real eigenpairs with the eigenvalue larger than 1 in magnitude. We need to take the corresponding eigenvectors and do some just addition of entries in order to obtain a Euclidean embedding of the nodes. We then cluster in the Euclidean space using your favorite Euclidean clustering algorithm, for example, k-means. Based on that clustering, we're actually then able to re-estimate the CKs. This can be done using a simple maximum likelihood algorithm. And then we go back to step 1 and we keep doing this until convergence or until we decide that we're tired. This alternating algorithm has a structure that you may recognize if you are familiar with things like EM algorithms, for example. And it is almost an EM algorithm, but there's a kind of this interesting difference, which is that EM algorithms optimize a likelihood, and this alternating algorithm actually doesn't. So it looks like an EM algorithm or an approximate EM algorithm, but to our knowledge, it isn't one. Anyway, that's a sidebar. Okay, so how does this look? Well, here's a little illustration of the pipeline. So this is one stage. We form this matrix J. We compute its spectrum. So I'm showing you the spectrum on the far left here, as well as the eigenvalues that are real and larger than 1 in magnitude. So in this case, there are 8 of them, and I've highlighted them in red. Then we take those eigenvectors. We need to kind of switch them around a little bit, sum them up to the level of nodes. And then from these eigenvectors, we extract features that I'm showing you in B. So here I'm just showing you for visualization purposes the signs of the entries of these aggregated eigenvectors. And we can see that some of these eigenvectors, so for example, y1 and y2, they're not useful for clustering. They are going to help us not at all when we are trying to do clustering. On the other hand, when we consider oh, seems like I can't spotlight anymore. Oh, well. On the other hand, when we look at some of these other eigenvectors, y3 through y8, we can see that the black lines, which represent the true partitions that I planted in this particular example, the eigenvector sign patterns have very different structures on different sides of these black lines, which indicates that if you use these to form a Euclidean embedding, then you would actually see these features approximately separating the nodes into clusters. And on the far right in panel C, I've shown you what that looks like. So here we have a pretty high dimensional embedding. In this case, it's a 24-dimensional embedding. But I've used a simple Tisney algorithm to simplify us down to a 2-dimensional embedding so we can visualize. And here, I'm not using k-means. I'm just showing you the actual planted clusters so that you'll believe me that if I did do k-means, I would get not necessarily exactly the right answer, but something approximating the right answer. Because in this embedding space, I can observe that my points or my nodes in the same cluster tend to be closer to each other in Euclidean space than they do to nodes in other clusters. So we now have a different algorithm. We started with modularity. We then moved to a non-backtracking approach where we formed this one big non-backtracking matrix, and we found that that was interesting and nice, but limited. And now we've proposed this belief propagation spectral approach where we approximate belief propagation in an alternating fashion using its linearization around an unformative fixed point. So how does that work? Is it good? Let's find out. So last time I showed you this plot, we had our plain spectral method based on belief propagation, and we got this new look like this, where we had kind of a sober looking performance, but we were kind of having some questions around the corners because we know that it's possible to achieve better performance there. When we move to our spectral algorithm based on belief propagation, on the other hand, we find a pretty exciting picture. So here's this algorithm in the same test bed. And an important thing to note about this algorithm is that in this case, we're running under the so-called Nishimori conditions. And what Nishimori conditions means, it's a fancy way for saying that we're assuming we know the right parameters to start with. So we're not doing an alternating algorithm this time. we're doing one round of spectral clustering where we know the parameters. And I'm going to show you a later example where we don't know the parameters, but here I want to emphasize that we're doing this under those Nishimori conditions where we know the parameters ahead of time. This is kind of standard in the literature. From a data analysis perspective, it's a bit of a cheat, but from the perspective of learning about the fundamental limitations, it's kind of the right way to move forward in the mathematical sense. So we can observe here that our belief propagation spectral method under the Nishimori conditions is detecting clusters correlated with ground truth. And you can actually check this, it's doing so in all the places where the Louvain algorithm was successfully detecting clusters, and it's also succeeding in all the places where our basic spectral algorithm was detecting clusters. So we are uniformly improving on both algorithms this way. And the fun thing about this is that you'll kind of notice some interesting features in this plot. So there's the region in which we failed to detect clusters looks suspiciously round. And there's this interesting little orbit around as well. And we can actually learn mathematically about what those are. So it's possible to analytically derive what this region in which the algorithm failed to detect clusters. We can actually derive its shape. It's an ellipse. And we can actually also figure out what's going on in this funny little orbit. It turns out that's about eigenvector collisions, or sorry, eigenvalue collision. I'm not going to talk about that. But I will tell you a little bit about this undetectable region here. When I say undetectable region, I want to emphasize that I'm stating a conjecture, but we have posed the following conjecture based on some theorems and some additional conjectured results. So conjecture, in a two-group block model with specified edge sizes and specified degrees, there's an ellipse in which spectral clustering fails to detect clusters inside that ellipse. So I've shown you that for a few cases. I'm showing you hypergraphs with edges of size 2 and 3, that's panel B, hypergraphs with edges of size 3 and 4, and with sizes 2 and 4, and varying the expected degrees as well. And so in all of these cases, we have this nice ellipse that characterizes when this algorithm totally fails to detect clusters at all. Additionally, we can actually treat that plain spectral method that was not based on belief propagation, we can treat it as a degenerate case. And so from these expressions, we can actually get boundaries describing that region of failure as well. So this is a conjecture, and so the proof requires some random matrix theory. It requires controlling precisely the spectrum of this non-backtracking or Hashimoto operator. And so this is a very rewarding, but also very difficult task that was beyond our scope for this particular problem. We have conjectures, we think we know what the right results are, but if anyone is a hardcore probabilist or random matrix theorist, then we would love for you to fill in the proof. So consider that one challenge for an open problem. Additionally, it's known that in graphs, when non-backtracking methods under the Nishimori condition fail, that actually coincides with complete undetectability in the sense that no algorithm can detect clusters. And so we pose the same conjecture here. We think it's likely the case that we've actually found the fundamental limits of this task. Inside that ellipse, as n grows large, no algorithm is going to be able to reliably recover clusters that are even correlated with ground truth. So that's a conjecture that, again, we have not proved. We're basing that on an analogy with what's known about the graph case. And if anyone is really, really, really into probability and wants to take a shot at proving that, then we would love to admire and later cite you. So please consider that a second open challenge. So this is the main story. This is the development of a non-backtracking method for learning about the clustering task in hypergraphs. And in particular, we found that through this method and through kind of some theorems about the eigenvalues of this operator, we're able to develop conjectures about when this problem is tractable at all for any algorithm. And again, I want to emphasize these are conjectures, and we would love for some of y'all to be the folks who develop proofs. I do want to show relatively briefly before I finish up, we can use this algorithm on actual data and learn something about actual data. So here's some data that I hope will be of interest to many of us. So here's an example of some data from Math Stack Exchange. This data was collected by Austin Benson's group. So what happens in math stack exchange is that we have questions, and these questions have tags. And so what we're doing in this data is we're going to treat each tag as a node and each question as a hyperedge. And so two tags, or any number of tags that are all applied to the same question, that's a hyperedge containing those tags. So here's an example. Questions on math stack exchange are not always posed in a very mathematical precise way, so I'm trying to replicate that. So maybe here's one question: does the derivative of a function at a vertical asymptote have to approach infinity? That's a question that involves calculus, infinity, and limits. On the other hand, we might have a question: proof that Fibonacci numbers grow faster than any polynomial. So that might have a tag: Fibonacci numbers combinatorics and limits. And so this would be the beginnings of a small hypergraph that we would build up with more questions. So this particular data has a couple thousand nodes in it. So what I've done is I did this clustering task in two ways. So one, using a non-backtracking method on the projected graph. So every hypergraph or every hyperedge replaced by a clique, otherwise same algorithm. So that's on the left. And then on the right, we have the actual hypergraph version that I've been sharing you, where we did not assume that we knew the parameters. We did several rounds of this alternating belief propagation spectral clustering, and we had a stopping criterion based on the k-means objective of one of the clustering steps in order to tell us where to finish up. So both of these methods recover some pretty reasonable and useful clustering. So for example, in purple, infinity, limits, radicals, and calculus all obviously go together. These are questions that are being asked by calculus students. Great. Love that. Both of these also recover some pretty reasonable other connections as well. So for example, combinatorics, generating functions, and Fibonacci numbers, those seem like pretty good things to go together. All make sense in both cases. On the other hand, the projected graph gets some things a little bit mushy and maybe makes some things that we would consider intuitively as mathematicians to be odd cross classifications. So for example, I'm sorry, I seem to have lost my ability to annotate here, so please do your best and be patient. If we look in kind of the center of the bottom area in the teal cluster on panel A, we'll see inner product space. So inner product spaces are lovely. That is, I would claim, obviously a linear algebra topic, but it's separated from linear algebra, matrices, orthogonality, cross product. Those are all in the pink cluster, according to the projected graph method. So arguably a miss cross classification there. Those should be in the same cluster, but they're not. On the other hand, the hypergraph seems to get this pretty much right. It has this nice, really well-defined pink cluster that we can kind of intuitively identify as a linear algebra cluster. It contains linear algebra, geometry, cross-product, orthogonality, inner product space, and matrices. And then in the teal cluster, it sort of collects everything, or a lot of things that we might think of as kind of general math questions that don't necessarily fit into the scope of a single topic. Definitions, soft questions, proof writing, terminology, intuition. So in this particular case, I want to emphasize that first, assessing the quality of clusterings is kind of more of an art than a science, and there are limitations on our ability to do that, especially by eye. And second, I want to emphasize that kind of our main emphasis in developing this algorithm was not to give state-of-the-art performance in any particular data set. But we do think that there's some reasons to believe that here the hypergraph structure matters. And so using a hypergraph non-backtracking spectral method actually helps us better understand the structure of the world of math topics as expressed in math stack exchange. So I'm going to go ahead and finish up. So the messages that I kind of want to leave you with today are first, belief propagation spectral clustering can help us form conjectures around when detecting clusters in hypergraphs is even possible. Proving these conjectures is likely to require some very powerful machinery from random matrix theory and discrete probability. If you're really into those topics, please have at it. I'd love to see what you do. And finally, the structure of the non-backtracking operator enables these kind of nice Ihara-Bass theorems, so we can make useful simplifications toward fast computations. So with those messages, I would like to close with a huge thank you to my amazing collaborators, Dr. Nicole Eichmeyer at Grinnell College and Dr. Jamie Haddock at Harvey Mudd. It is both a pleasure and a privilege to be able to work with them, and I learn a lot from both of them. So I'm really glad to have had the chance to work on this project with them. Again, this paper is on archive if you want to check it out. Otherwise, if there's time, I'd be very happy to take a few questions.
Thanks a lot, Phil. I think we do have 5 minutes or so to take some more questions. So does anyone want to start us off, either in the room or online? Nico?
Oh, I can go. Hi, Phil. Thanks for the great talk. Just a question, a naive one regarding belief propagation. So when doing classical belief propagation, we're always told, or at least we're aware, that loops can be a problem in graphs, right? So I was wondering, does this translate into any other kind of issues in this rather dynamical system and spectral approach?
Yeah. So in order for belief propagation to work in this kind of setting, what we usually do is we sort of make use of large sparse heuristics that can be made precise. And the idea is that in a large sparse setting, graphs and also hypergraphs are locally tree-like, and this is considered locally tree-like, and this is considered justification to believe that belief propagation is going to do well. We actually also use this assumption when proving the theorem that I put up here in order to get this linearization result, and in order to prove that the other entries of the Jacobian are negligible as n grows large, you also need to make these sparsity assumptions. And so there are some assumptions that I've kind of swept under the rug here in order to motivate the idea that belief propagation is a good thing to do. But in some sense, you only need to accept sparsity in order to accept this theorem. You don't actually need to accept locally tree-like. You can kind of take that for what it is. Fortunately, actually, one of the reviewers for this paper did point out that there have been some reasonably precise proofs about local tree-likeness in the literature. And so we learned some things about those and cited them in the paper. So if you're if you are justifiably questioning that phrase, then check out our references and maybe we can all learn something.
All right. Okay. Thanks. Thank you.
Yeah.
Hi, Phil. I have a question. First, thank you for the talk. I am a little bit curious what will happen if you have really huge edge sizes. So currently, I see that in your formulation of both the nonbacktracking operator and this J matrix, you need to be correlated to the number of edge sizes. And if you have, for example, size 100 or even larger, then will this be problematic to the algorithm?
Yeah, so I think it depends on what you mean by problematic. On the one hand, there's essentially no reason that this algorithm would fail mathematically due to large edge sizes. However, both J here and this related operator J prime, they do depend. It's actually not about the large hyperedges. It's about having a large number of distinct edge sizes. So if you have a hypergraph with edges of size 10 and edges of size 100, that's only 2 distinct edge sizes. That's actually not really going to be an issue computationally. But if you have a hypergraph with edges of sizes 2 through 100, that's going to be a challenge because these matrices are going to get pretty large. You're also going to, I think you're going to see, and this is actually speculation, but I think you're also going to find that it's going to be harder to reliably estimate the statistical parameters unless you have a large number of edges as well. So yeah, I do think computationally there are going to be problems there. In some sense, so theoretically, no, computationally, yes. Again, one thing I want to emphasize is that we like this algorithm, we learned from it, we think it's good mathematically, we think that it tells us some useful mathematical things. It's not our claim that folks should use this algorithm for data analysis most of the time, because it's going to, I think, be pretty good for relatively small data sets, but we've actually seen some experiments, which I could show you, but I haven't yet, where, for example, it gets outperformed by a simple modularity heuristic on some well-known data sets, for example. So we think it's a good algorithm. We think it's good for a lot of sort of theoretical questions, and we learned a lot by doing it. It's not our claim that this is state of the art for large complex hypergraphs in terms of raw performance.
Is there one more? I think we have 1 minute. Yeah, please.
Thanks for the interesting talk. Actually, it's not a question, maybe some comment. So looking at your Jacobian matrix, there is kind of like a mathematical trick called the master speed function, which might be useful for you to analyze, to simplify your Jacobian analyze.
I'm sorry, could you say the name of that again? I'll look into it.
Master stability function, MSF.
Oh, master stability. Okay.
Yeah, so maybe might be useful for you to simplify your Jacobian.
Yeah, thank you for the tip. I'll look into that.
Oh, I see something in the chat. So there's one in the chat, Phil. For the synthetic testbed, did you compare the detectability region for belief propagation on hypergraphs with belief propagation on projected graphs? And does the discrepancy increase with increasing edge sizes?
Oh yeah, love this question. So this is a really nice question. I'm weirdly not able to look at the chat, so I'm going to be going on what Tim just said. That's all I remember as best I can. So yeah, we didn't show that experiment here, but we did actually look at that. So on projected graphs, the plot actually looks very similar to this one. And if I remember correctly, it might even be exactly the same now that I remember. It's been a little while. What happens for the projected graph is, so you do this spectral algorithm, but before you do the spectral algorithm, you replace all the hyperedges with cliques. And then you just do standard graph non-backtracking spectral clustering. And the result looks very similar to what we've shown here. And I think it actually, I want to say it's actually the same, but don't quote me on that. I think you can actually show the detectability threshold is the same. So in some sense, there's kind of this intuition. Aggregating, again, I think this is right. Having a little trouble remembering here. I think this is right. When we do the pure spectral method based on the non-backtracking operator B, the big one, then that actually has the same performance as a projected method where we do a clique projection. And so in some sense, we need to use these kinds of belief propagation methods in order to realize the benefit of the higher order representation. I think that's right. It's been a little while, so I could be misremembering this, but I think that's right. The plot definitely looks qualitatively like this. I can say that much.
Great. Well, thank you so much again, Phil. Let's thank Phil.
Yeah, thanks so much, everyone. It's been a pleasure.
Yeah, thank you. And if people have more questions for Phil, you can check out his website, check out his papers, and communicate with him via email. And yeah, thanks so much for being our first speaker of the term, and we'll see you all next week, same time, same place. Thanks. Thanks a lot, Phil. Oh, hold on, my audio is not right. Oh. Okay, now I think it's better.
Tim, was there something you wanted to talk about at some point? I feel like I remember you saying you wanted to talk about like configuration